Okay, welcome everybody. Is the volume okay? I think I'm scared of echoes, but wait, there's a mic on over here, so I should turn that off. Oops, so it is off. Okay. Well, if I keep away from the speakers, I'll be okay. Okay, so yeah, so welcome to this day session on control systems and reinforcement learning. And let me thank Aditya and other organizers for putting this together. We're really grateful. Yeah, so there's three parts to this. Today, parts 1 and 2, will be about, well, let me just say first part 1. The title here, Algorithm Design Dynamical Systems Approach, that's stolen from Vivek Barkar's book on stochastic approximation. And so really, I'll be talking about stochastic approximation, and it'll be more exciting than it sounds, I promise. And there's some new discoveries actually since the book, which I'm quite excited about. This is an image, which unfortunately is not big enough, of some of the beautiful springs around Florida, around the University of Florida. It's the prettiest part of Florida. The south sucks. The north is really beautiful. And that's the new book. And by the way, if you wonder what that cover is, it's actually a randomized policy that came out of some stupid experiment in 2008 or something. And that's the thing, is that I've never gotten reinforcement learning to work on any QA network example, but a complete stupid hack, idiotic, resulted in this distributed control law that's just perfectly reasonable and wonderful, and yet there's no theory at all to support it. I'm not going to talk about that, but it's just wild how hacking is the way to go sometimes. So here's the three parts. So first of all, I'm going to talk about the OD method basically for algorithm design as defined by the Russians in the 60s, that you create an algorithm as an ODE, and then you translate it to a discrete algorithm. So Leonard Leung promoted the opposite direction in the late 70s, 80s, saying, I've got a complicated algorithm, let's look at an ODE approximation. No, Leonard, I love you, but you were wrong. So the Russians were pushing that point of view way back. And that's the point of view in the book. So then I'm going to go through and basically follow up on Deb's lecture yesterday and talk about Q-learning, the basics, and some new results on when it works, and how, talk about sources of instability and how to fix them. And it's what's really fascinating is the key takeaway there is that exploration stabilizes. So exploration is, this epsilon greedy business is usually promoted as a way to efficiency, because you don't want to sample state action pairs that are obviously dumb, but in fact, it turns out that it stabilizes, and that was a breakthrough a couple of years ago. And then tomorrow I'm going to talk about actor-critic methods. The schedule's changed. I think it's the morning, and it's a very personal take on this stuff, and it'll be really interesting to have a discussion about when I'm done. So in terms of resources, I mean, I'll say more, but this is all chapter 8 of my book. And I really like this. If you don't know stochastic approximation very well, I think this is a really good introduction. I don't have a lot of proofs. I give lots of references, but it gives you just the main concepts of why things work. And there's some sort of tutorials that I'll go through to sort of get, help you along. And then, I'll talk about this later, but MDP theory and actor-critic methods, this research. And sometimes I have to be really defensive because anybody can get out of bed, type in ChatGPT and get something working. But, I think, well, this DeepSeek thing is maybe, it could be fraud, but it's maybe evidence that a little theory goes a long way. That instead of 47 days to train the, a chess program, maybe you could do it in 3 days if you understood the theory better. And I still have hope that's true. Even though I just said hacking has so much value, hacking has limitations as well. But anyway, and the thing is that there's real problems with the whole field of RL, that it's so singularly focused on methodology, optimal control, MDP theory. But there's such a rich collection of tools. It's, you can adapt them to your needs. So I believe in that as well. And So what's left out is I'm not going to say a lot about exploration. I am going to say something because I'm going to talk about how it stabilizes, but it's a field in itself. I mean, the entire workshop's devoted to Thomson sampling, for example. I'm not going to mention it. And I'm going to focus on the theory of actor-critic methods. And the theory I will present is so mathematically elegant, it makes me cry. And it's so worthless, it's incredible. It's a bit like Shannon's theory of coding, that it was just elegant, but you couldn't use it for anything. You needed you need computer engineers and other mathematicians to come in and make it work. You know, this is disconnect between theory and practice. It's so vast. It's depressing as hell for me. I'll explain that tomorrow. All right, so today, algorithm design. So I'm going to talk about the OD method, and I'm going to give you some rules which you must follow. All right, and I'm going to violate anything you've ever heard if you came from a CS background or you came in from an optimization background. You'll say rubbish, but I can back myself up. All right, never, ever, ever in RL in a stochastic environment should you use a fixed step size. There's no motivation. There's no reason for that. None, none, none. It's so hard to choose the right step size if it's constant. It's so trivial to choose an optimal step size if you know the theory well. Okay, so I'll talk about that. Now, the thing is that a real issue in RL is that Q-learning outside of what's called the tabular setting, there's no stability theory at all, except for some, if you hack and hack at the algorithm, you can create stability and end up solving a different problem. And one way to universally stabilize is something called ZAP, stochastic approximation. It's a joke. ZAP refers to Zapdos, the Pokemon character, if you know Pokemon. And I'll tell you the history over drinks if you like. All right. Okay, so anyway, this is just, I'm not going to go through all this, but there's a bunch of resources you can look at later on. And I mentioned this book of mine that came out a couple of years ago. This networks book has a lot of nice theory on TD learning as well. And actually, it's again depressing as hell because I wrote the book thinking I was going to get an architecture for reinforcement learning, and then I never got a single successful example. And so the last chapter is about simulation RL, and everything's negative. And that's a hint I'll talk about. That there's a problem in queuing networks that I'll discuss. But anyway, I find it a useful resource. And of course, there's the Markov chain book. And so, yes, so in terms of co-authors, I'll never, continue. I mean, I'll always thank Vivek. My first sabbatical was in India and Bangalore, and what an incredible mentor. I know his book is hard to read, but he's an absolute gem. Incredible scholar. And my buddy Prashant Mehta, I forgot who he is. What, do anybody remember? Anyway, he's at IIT Bombay. And Giannis and Anna and Eric and Aditya. And then it says here graduating in May 2025. Where are you back there? He's actually graduating in August. And he most likely has a postdoc, but the way things are going in the United States, it's not certain. So he's an awesome student, as he knows. And if you're looking for postdoc, he's a gem. Yeah. So in terms of goals, we'd like to solve different kinds of problems. What are they? An example, number one, is just computation. Markov chain Monte Carlo, which was the biggest interest of my friend Richard Tweedy back when we wrote the book on Markov chains. And it's just this boring integration problem. We just like to integrate, a function, in this case, a special form. We've got a density times the cost function, but just think of the product as some positive function. And how do you perform numerical integration in high dimensions? I don't think it's worked. I don't know if MCMC is really the solution. It's still a work in progress. But the idea is, you generate a Markov chain whose steady distribution has density F. In fact, it's unnormalized density, so that's part of the issue. And then you just do Monte Carlo and you get estimates. And if it's a nice Markov chain, the law of large numbers holds and this converges with probability 1. Okay. And alternatively, you can apply stochastic approximation. Okay, so you have, here you're just doing the sample average that you're all used to. here, this is actually a, you know, Richard Sutton would call this the, what's the term again? What's the term? The something signal, oh, it'll come to me. I'm tired. Anyway, it would be the excitement signal. He has a name for this in the 80s. All of his work, it's he takes some psychology. Somebody remind me. All this called the excitement signal until I remember the real name. but this comes up in RL as a thing. Really, you want the mean of this to be 0. All right. So it turns out these are equivalent with the right choice of step size. So if you take the step size to be exactly 1/n, these two guys are equivalent. And the proof is really trivial. You just take that, multiply both sides by n, and you get a recursion, which turns out to be this exactly. So Monte Carlo is a special case of stochastic approximation. And then you could say, let me figure out what the optimal step size is. And maybe I'll use Adam. I'll use whatever. Well, it's 1/n. I mean, if your goal is to minimize variance, it's 1/n. But you could say, I don't care about minimizing variance. I want a finite, n bound. And good luck. All right, so here's where I'm not being aggressive, I'm being assertive. Good luck. So over here, if you're in the sort of CS community, well, I'll give you some advice. If you want a rejection from NeurIPS, write an RL paper without a finite n bound. It will be rejected, right away. And I want to fight back right here in front of all of you. So this doesn't exist for a damn Markov chain, a finite state space Markov chain. Yeah. You can get a I of epsilon, but it's going to be like epsilon squared divided by the alphabet size squared or something, or to the 5th. I mean, you get something so conservative, it's meaningless. And it's because of the fact that it's the Markov chain, if you remember Jordan decompositions and all that, eigenvalues don't mean much unless you have a reversible Markov chain. So for a reversible Markov chain, you can get something which is relatively tight. Okay? Outside of that, you can't. Now, what if it's not a finite state space Markov chain? Take an MM1Q. An MM1Q is just an example of reflected random walk. So what do you think you get here? Stable. So MM1Q is reversible. It's geometrically ergodic. It's got every property in the world you could imagine. It's the most wonderful thing in the world. Guess what I of epsilon is? 0. You know what you have to do to make this thing work? You have to replace the epsilon by epsilon times n. So if we can't get a finite n bound for Monte Carlo for an MM1Q, why are we pretending we can do it for these complicated algorithms? Okay, so what ends up happening in the RL community, in the mathematical RL community, is that algorithms are designed so you can get a finite n analysis. It's just awful. Now, in terms of, if you're looking at variance, then there's some hope. And Srikant had some recent work. And if you're looking at sort of the central limit theorem type results, like the central limit theorem holds for an MM1Q beautifully. And then if you can get refined central limit theorem bounds, then there's hope. But you cannot, we just have to, they've got to stop rejecting papers just for not having these results, which are typically not going to work. So that's happened to me several times. I'll be like, every time a NeurIPS paper is submitted, I'm asked why I don't have a finite n bound. All right, so that's my one example of me whining, and I'm being assertive, not aggressive. Right. I think in their place, they're awesome. In Bandit's literature, it's amazing, the impact and the beauty of the Bandit, of the finite n bounds and how they've been used. It's just in RL, I think it's vacuous. It's my belief. Okay. All right, so then there's optimization. And here's a ridiculous objective function, this Rosterkin function. And we'd like to find the minimum of this. I should, yeah. I mean, I'll be here. I should put a theta here. Yeah, I can't use, I used eta here for the Monte Carlo runs. I'll call it theta. So theta, I'll use theta for parameter estimates. There's going to be this notation I'm going to have is that I'm going to have some function of a parameter and some exogenous noise. And in this case, it's just this boring thing here in the stochastic approximation equation. That thing is this f. And with theta fixed, if I take the mean, that's what you'll see called f bar of theta. And in Monte Carlo, we would like to set that equal to 0 because we want theta to be equal to mean, let's see, which is what I call theta. So I'm going to give lots of examples of f bar and f. Yeah. So in optimization, of course, if we want to try to find a minimum, you look at the sufficient condition.
Sorry.
Oh, yeah.
I think your mic is
Oh, is that? Oh, okay. That's really good.
also recording. It will be quite bad.
Oh, yeah, thank you very much.
Yeah, that's good.
Yeah, I'm too much in my head. I'm not hearing the noise. That's better. Thank you. It was creating stress without my me being aware of it. So we all know the first order condition for optimality is the gradient is equal to 0. And I'm telling you, my goal is always to set some function equal to 0. So there's my f bar. It's going to be that. So stochastic gradient descent is where you do gradient descent, but you tag on some noise, and you do that to avoid local minima. And this is an example which really falls outside of this lecture, because if there's multiple solutions to f bar of theta star equals 0, then my rules that I'm telling you about don't apply. This is an example where you do want a non-vanishing gain, step size probably, because you're trying to not get trapped in any of these infinite number of local minima. All right, so just be warned there. And we get to design this noise, this disturbance here, anything we want. Commonly, IID is used, independent and identically it's distributed. I don't know if that's a good idea. I'm going to argue against that maybe a little later if I have time, but you have a choice there. Another thing is these zeroth order methods. And one example was introduced by Spall. It's a simplification of what's called Kiefer-Wolfowitz. We're doing approximate gradient descent without access to the gradient. And so you have some approximation of the gradient here. You can still add on some noise for exploration to avoid local minima. And you have this weird thing here. You take an IID zero mean vector sequence here. So this CN is zero mean IID. More assumptions could be helpful if you like. The mean of this, with theta fixed, the mean of this is approximately equal to the gradient, with an error of about, depending on your assumptions, like epsilon squared. Okay, and so this works really well if you're clever in your choice of this exploration signal. Here's an example where the theory pushes for IID, and Caillou and I have argued that that's a bad idea. You could do much better without that. And so the fact that we get to choose these signals here and here is really valuable, as well as as well as designs like that. Okay, cool. So, but again, this is a case where all my rules do not apply. Okay, I don't know how the best choice of step size for a problem like this we have local minima. And I don't think anyone does. It's still a research topic. Like simulated annealing, it's still an open area in a way. And the reason for gradient free is one example I love is optimizing wind farms. I mean, it's actually a lot to be gained by changing the pitch angle and the angle of the turbines, everything. And there's no way you have a good mathematical model. And there's no way you have a gradient from that model to get a gradient. And so you can just observe the amount of power being generated and make these things swing around and self-optimize. And I think it's pretty cool. And it's there's research being done on And also all the actor-critic methods create an approximate gradient. And they do, and the whole, what I say is such beautiful theory, is actor-critic methods allow you to construct an approximate gradient where the bias is zero. The mean of this is zero. So you actually get true gradient descent, just as if you had the gradient, which is just absolutely elegant. And so I say here, it's zero. This is mean zero in a weak sense, meaning that if I fix theta n from the definition and take the mean, I get zero. The fact that theta n is varying causes some bias in the transients. All right, so we'll talk about that tomorrow morning. All right, but of course, I'm not just talking about gradients. There's almost no example in RL. Well, except all the temporal difference methods in RL, except for one, they're not about gradient descent. Even though you hear language like semi-gradient descent doesn't really mean anything. It doesn't, it's nothing like gradient descent. We just have root finding problems. And, we saw Deb talk about, these two functions yesterday, and I'll talk about them in the next hour. The dynamic program equation leads to a root finding problem, and which I'll explain. But this, you hope that there's an F bar that we will construct, and by setting that equal to zero, finding the root, the goal is that will approximate the solution to dynamic program equations. The theory is completely lacking so far, but it works in practice. It just almost always works in practice, as far as I know. And so we'll get into that. And so this is the most important. This is what we'll focus on, in my 3 lectures, or at least today. Is these, I want to give you a theory of stochastic approximation, algorithm design with this, Q-learning and temporal difference learning in mind. And yeah, okay, and that's what this is. So here it is. Just saying it all again. Our goal is, whatever the problem is to solve a root finding problem. That's it. And step 1, again, this is the Russian school. There's a history in the book in chapter 8. So, design a ODE. See, F bar is designed for 2 things in mind. It approximately solves a relevant problem, and this ODE is stable. So you gotta design for both. And globally asymptotically stable means in particular that the solution to this ODE converges to some unique theta star from every initial condition. And it's that uniqueness that implies the rules I'm going to talk about. Without uniqueness, you gotta rethink. Therefore, I'm assuming F bar is Lipschitz continuous, and so therefore F bar of theta 2 converges to 0. Okay. All right, and then one could do an Euler approximation. If you had access to F bar, nobody wants to solve a differential equation. You could do an Euler approximation, but as Polyak, pointed out, and many others, you don't have to use an Euler approximation. So you could do all sorts of funky things here to get a better solidarity with the ODE. But you don't, whatever you've done, whether it's Euler or something more complicated, I'll stick to Euler, but you don't have to. You then say, well, I don't have access to this. Just like in Monte Carlo, I didn't have access to the mean of C. That was what I was trying to estimate. So you replace F bar by this stochastic observation of it. There's this noise sequence here that it came up in this 0th order optimization techniques. This is a random, the mean of this in some sense is equal to this. And that's a picture of Robbins from the 50s. And this is the Robbins-Monroe algorithm. Okay, so this function is designed so it's equal to this plus noise, which at least asymptotically is 0 mean. So C is a ergodic Markov chain typically, and then the steady state mean of this with theta and fixed is exactly. I'll be very precise as we go along. But the thing is that we already know that under conditions in F bar, Euler schemes work, you know, and the whole proof that they work is the fact that there's a robustness in under assumptions on F bar, on the vector field. There's a lot of robustness in the Euler approximation, and the robustness is so extreme it can handle a lot of noise. So this noise can be massive, and still you get the solutions to the ODE and the solutions to this couple for long periods of time, you know, and that's it. That's how you end up proving convergence. So here are the things that we have to do in our design. So I said we have to design the dynamics. Again, I said we're going to design for GAS, global asymptotic stability. I'm not going to define that, I don't need it. But in particular, it means that any solution to the ODE converges to theta star as d goes to infinity. But really, we typically get more than that. We get what's called exponential asymptotic stability, which is easy to define. It just means that there's exponential decay in the initial condition. So I mean, every example in RL I know, if you've shown stability, you have exponential asymptotic stability. And moreover, typically this implies it, but moreover, I want the linearization at theta star to be a Hurwitz matrix. And that always holds in every example I know in RL for which stability has been shown. And Hurwitz means that the eigenvalues of this linearization are in the strict left half plane. And it just means the linearization is stable, you know. It just means that if I look at if you look at the linear system, its solution is a matrix exponential times the initial condition, right? And Hurwitz, this means that this goes to zero. When the initial condition goes to zero exponentially fast. And the reason this comes up is what you end up doing the analysis is you end up linearizing the ODE. So when you want to get fine results, like if you wanted to prove something like a Finan bound or a central limit theorem, you would linearize the dynamics and use the fact that uses exponential stability to get the results you want. That's a standard, you know, tool in the analysis. The other thing you've got to do is assume Lipschitz continuity. And this is something that gets missed sometimes. You're dead if you don't have this. It doesn't work. The robustness I talked about with Euler approximations doesn't hold anymore. So make sure this holds. So that this means that if I look at F bar evaluated at two different thetas, it's a fixed constant, so the difference is bounded by that fixed constant times the difference in thetas. Example, Q learning for LQG. This fails. Okay, it turns out you end up with a quadratic nonlinearity, and so it's not going to work. You've got to do something to fix that, you know. And there's ways to fix that. Yep. Q learning with just standard Q learning for the LQG problem, you know. Yeah, because there's a minimum in the Q learning algorithm, and that minimum, when you solve it, gives rise to theta squared. So you get a quadratic nonlinearity. And so if you run it, it's just going to blow up. It just won't. Euler schemes just don't work if you have a quadratic nonlinearity. And you can fix it though, as we will discuss. You know, I'll give a simpler example. Yes, yeah, here it is. Here's an example. So the reason that Spall's this version of Spall's algorithm has not been very popular is because it blows up. If you think about a typical loss function, so gamma is my loss function I'd like to minimize. Imagine it's a quadratic, right? I'm just trying to minimize a quadratic. Well, this is the thing that appears in my algorithm. I've got, even though it's approximated by a gradient, which might be Lipschitz, the function itself is quadratic, and so it's not Lipschitz. And if you run it, it'll blow up. At least, I mean, under the assumptions of Spall, that this C is IID. So what do you do then? You know, what you can do is you can change this little epsilon and allow it to grow with theta. Problem solved. So you basically stick something in here which grows linearly. Like if gamma has quadratic growth, like if Lipschitz if its gradient is Lipschitz, then you can plug in something here which grows linearly with theta. This becomes a Lipschitz function, and you're solving the same problem. Basically the roots are the same. And so you could do the same thing with LQG. You could basically take the right-hand side, divide it by something with linear growth, you get something Lipschitz, and it would work. Maybe not very efficient, but it would fix the problem. I've never tried it for QLinear. Okay, so yeah, one example is you basically have some prior on the minimum, and you take some smooth approximation to the distance to that. And that sigma squared is some notion of uncertainty in that prior. You could do all sorts of things. All right. Yeah. Because the math is so elegant. Yes. I mean, it's just, oh God, I mean, it's incredible how simple things become in continuous time. It's like if you look at TD learning continuous time, it's a simple linear ODE, and it's just go, obviously it's stable. It's wild, and really it's true for TD learning as well. Like in the tabular case, it's very easy to see it's stable. And I'll give examples where you can go monkey around and stabilize in the continuous domain. You'd never imagine that in the stochastic discrete domain, that you could get away with it. Yeah, absolutely. So you just start and design continuous. Of course, at the end, you have to translate. Yeah. So here's a funny rule. So here's the standard assumptions that you'll see in Burkhart's book, everyone, since they were born. So the step size that appears, the summation of the step size, I better keep this up here. Step size. Okay, learning rate or whatever. So the first assumption is clear. I have to get somewhere. Think about the Euler approximation. The partial sums of alpha n is like dt, and I need the sum of dt to be infinity so I can get somewhere. The second assumption is kind of weird. It comes out of a particular method of proof. And a typical example that's pushed is this, which I like. You just take some constant, some initial NE plus n to the rho. And rho would have to be between 1/2 and 1 for the second assumption to be valid. Okay. Again, it looks like it's necessary for this traditional model, which is the focus of Burkhart's book, where this F is just F bar plus real noise, which is zero mean, actually martingale difference. And if you look at the proof, it looks like, well, of course you have to have this. It's how you kill off this martingale term. Okay. Well, we discovered last year, Caillou, no, you don't need it. It's a method of proof that leads to that assumption. If you change your method of proof, you realize you don't need it at all. And I can explain in 1 second. What you do is you look at Zn. Not squared again. You look at a normalized error with a square root in there, right? And I don't try to show that, well, forget that for a second. I mean, the standard proof, you're just trying to show the error goes to 0, all right? Let's forget that. Let's look at this normalized error. And what you end up doing is look at this normalized error and show that it approximately solves a linear ODE, right? And from that, you show that the expectation of Zn to the pth power, sup over n, is less than infinity for all p. Can anybody see what that implies? it means that the pth moment of the error is bounded by this to the pth power. So if this is summable, that's summable. And I could use Fubini's theorem, and I could say that the sum of this is actually is finite, almost surely. So I get that this goes to 0 and it's actually summable. And so you just need the alpha into the pth power, p over 2 power, to be summable for p large enough. Now we've only looked, we stuck our theory stuck to the case of 1 over n to the rho, but I'm sure it's general. I mean, I think that it's generally true. You need some assumptions. Say for a finite state space Markov chain over here, you don't need a assumption at all. It does influence bias. Okay, so if you take alpha n going to 0 very, very slowly, then the bias will go to 0 slowly. And so you could end up having this situation where bias is worse than the variance. And so, having high gain in some applications is useful. And in the second hour, I'll give an example of that. And here it is. You see, you get that the covariance of theta n divided by alpha n goes to some matrix you can identify. The bias divided by alpha n goes to something you can identify too. If that's non-zero, then the bias can go to zero very slowly if alpha n is going to 0 slowly. So it conceivably can be a problem in some cases. It's not like we really want to find theta star exactly anyway. I mean, some bias is not going to kill anybody, But anyway, but any additive noise model, this thing is 0. So if in stochastic gradient descent, the standard varieties, you don't have to worry. There's just no reason not to allow rho to be 0.1. Now, rho equals 0? No. No. Why? Why would you? If there's a unique theta star, why would I use a constant gain? Somebody in discussion, let's have a debate. I don't know any motivation at all, because the rate of convergence is slow as hell. The motivation for constant step size is in deterministic algorithms. You get linear convergence. Theta n goes to theta star exponentially fast. Theta n goes to theta star like at best like 1 over square root of n, maybe a little faster. So if that's the case, then why would you worry so much about fixed steps, constant step size, which is so hard to design? It's really, really tricky. So just slap in choose your rho that you like, 0.6, and you're done with it. You don't have to think. Isn't that liberating? No. You don't have to obsess about step sizes anymore. Just for or all, optimization is a different story. Yeah, I mean, deterministic optimization, deterministic. All right. Okay. So basically going through some rules, we went through a rule about how to design the dynamics. There's a rule about step size choice, which is basically says you're free, just don't take a fixed step size algorithm. And the last thing is you've got average. You just you're forced to, and nobody's come up with anything better than this completely naive Monte Carlo average. So Rupert in the US and Polak in Russia came up with this roughly the same time. Take your estimates and maybe throw away the first n0 steps because of all the noise, the transients, average the rest, and magic happens. They assumed, the assumptions of Polak require that rho be strictly between 0.5 and 1. We've shown that's not true to some degree. Maybe I'll explain. Oh, we don't need that. You could actually let rho be 0.1 and this covariance result. But you see, for the original parameter estimates, I'm saying that this has a bounded pth moment. So the convergence rate is like square root of alpha n, which could be very, very, very slow. Alpha n could be n to the 1 over n to the 0.001 or something. And it's an incredibly slow convergence. All you have to do is average, and you go from a rate of convergence of alpha n to 1 over n. It's completely wild. It's something so trivial can do so much. And not only that, that matrix is minimal. You can't get a smaller matrix in a matricial sense. So yeah, so let me just, I've got a list here. So, the bias would blow up if you had rho equals 1. So you've got to have rho less than 1. Also, well, you see here the covariance decay is like 1 over n. Okay, and then this is minimality. So that sigma theta star, if you took any other linear system, some wild thing that took that function f and did all sorts of funky linear transformations and all sorts of averaging or whatever you want, I think even nonlinear, as long as there's a linearization at theta star, you get a covariance which is no less. This is minimal. So you get so much from averaging. So you have to do it always. All right. Otherwise, you fail the course. All right. So 3 rules. All right. Is that clear? This is a really important point. Yeah. And I'm just trying to the simplicity of all this. I mean, the fact that, yeah, the hard part is step 1, making sure you've got Lipschitz continuity, exponential stability, all those properties. That's really hard work. And after you're done with that, you don't have to think. Slap in this silly step size and average, and you've got the best performance you can. Oh, it's just an extra term for you to play with. The idea is that this would be roughly constant up to the time. So if you graph this, it would look roughly like G over NE for well, and then the curve down. The next degree of freedom. Yeah. Yeah, the value of NE and G are arbitrary. But what's going to happen in practice, like if you chose NE to be 0 and G to be big, the thing will just blow up initially, And I think, yeah. And then I'll say what to do then, because you're going to get some awful transients if G is too big. But because then you should go back to deterministic theory. The Lipschitz constants come into play. Those of you who have taken courses on optimization have seen, looked at fixed step sizes and how delicate the choice is, and so the transients get hit. But we'll talk about that in a minute. We actually have a formula for this covariance matrix. This sigma theta star that I mentioned, it's the linearization matrix that I talked about before, and it's some weird covariance matrix times the transpose inverse of A star. And this is some weird thing. What I do is I take this stochastic process here, evaluate at theta star, and I'm going to assume that Cn is a nice Markov chain. Okay. Now this has 0 mean by definition. Okay. Because the mean of this is f bar of theta star, which is defined to be 0. And so this here is the power spectral density evaluated at 0, which would be the covariance in Monte Carlo. If you were averaging this sequence, it would satisfy central limit theorem. The covariance matrix associated with that is in this. And so you can imagine where this linearization is coming up. This is, it's basically, you end up writing down approximating this recursion by, well, I'll write it down. There it is. You basically, you take that approximation, you justify it, and that's how you end up getting that averaging gives you this. I mean, the proof is really, really short. Once you justify this approximation, the proof that this happens is just nothing. It just pops out. See, that's the thing. This is where, again, I get into trouble. I mean, it shouldn't be controversial to say I like the center limit theorem. But, but that is, I mean, I think it's getting better over the last 5 years or so. But even mentioning the center limit theorem used to get you into trouble in NURBS because it's asymptotic. You never know. You don't have the assurance of a finite end bound. Center limit theorem is this weird asymptotic result. But when you do repeated runs, you will see a nice little Gaussian histogram. And from a bunch of short runs, you can estimate the center limit theorem variance, this scalar example. And empirically, it works really well. And so far, we don't have any other tools. So if you want to try to get an estimate of how long you have to run the algorithm, the only method I'm aware of is you do multiple short runs, get a little plot, approximate the CLT variance, and then you have an approximate confidence interval going forward. And you're not going to do that. You're not going to estimate A star and estimate that covariance matrix. The only way to do it is to just do repeated runs, knowing the CLT does hold. All right. Yeah. Now, I don't know if I even should do this. By the way, I'm not going to go through the pages. And a lot of those are references, but there's more assumptions, which I'm not going to go through, I don't think. Forget this. I will brag about the fact that we can deal with general state spaces, and we don't even need this thing to be Markovian. It can be a parameter dependent stochastic process. That's only a year old, and we get all these really nice results. Yeah, but so forget all this. This is another rule: never have a slide like this with so much text and garbage. But for a model like this, just take it to be finite state space. Okay, the F bar then ends up being a finite state space. You'll have a invariant probability mass function for each theta, this transition kernel, and F bar is just the mean of that. And here where there's a big apology, I know that pi is now used for policy. In my lectures, it's not, because I've used pi for invariant probability measures my whole life. When I was 5 years old, pi was an invariant measure. So I'm sorry, but pi for me will always be a probability measure, a probability mass function, not a policy. But anyway, that's F bar explicitly for a Markov model like this. All right, so yeah. So what I want to do is I'm going to go through an example and just show you how the rules come into play, and where the step size choice is important or not. Explain these three figures. So this is like the middle of chapter 8 of my book. I'm just taking that out. All right. So where is it? Erased. I think that, oh God, yeah. There's a mistake here. This should have been first. So this tau n, which is a sum k equals 1 to n of alpha k, that's the integral of dt. All right, so that alpha k is like dt, for the k sampling interval in an Euler approximation. So tau n would be the natural time scale for the ODE. And so I'm looking at the ODE, and I'm trying to compare it to the recursion. I would have to compare theta n to this other theta tau n and divide that by square root of alpha n, which is what's occurring here. And that's going to be a practical Gaussian for large n without averaging, just looking at that. And here's where you can really see an issue with step size, where it really is important. Well, right there, yeah. So this tau n, which is a sum over here, it's going to be, with this, again, I'm going to stick to this step size choice. It's going to, if rho equals 1, it's like log n. So it's just crawling ahead. That's the problem with 1 over n. So if you look at Watkins' original paper, he proposes a step size, which is roughly like 1 over n. No, never do it. Never use 1 over n as a step size. And the reason is right there. That log n growth is just too slow. If you take a row that's smaller, then you'll get this n times alpha n. That's going to be blowing up much, much faster than log n. And so, you know, so that's going to be helpful. So here's the thing. So as I said, we're going to design this ODE with exponential asymptotic stability. So we have convergence of the ODE exponentially quickly. When you plug in this tau n, you can screw that up completely when rho equals 1. But this is a bit dated now about gain selection being complicated. That is before our recent work. So, but there is a point there. So if you really are obsessing about gain selection, I'll make that clear. So again, if we were going with a 1/n step size, that's why this is a bit dated. Because now I'm saying never use 1/n. But if you were using 1/n step size, then if you're far from theta star, you might need a large g. When you're near theta star, a small g. And you would really end up having to create something like atom, where you have this adaptive g, which is completely complicated and not needed. Right? So just don't do this. So here's an example from the book. So it's I've got this strange objective function, which was just created just for fun. It's just nothing useful at all. So I've got this quasi-convex objective I'd like to minimize. I've got my f bar is minus the gradient of the function, which was designed to be wiggly like this. And it was designed so that it's sort of, looking at a large, far away, its slope is like -1. But looking locally, its slope is -4. If you were thinking old school, you'd want a small g if you're far away. No, a big G if you're far away, and a small g here because of the steep slope. And those conflict. So if you went back to the work of Rupert that I mentioned, he would have completely said, you've got to go and analyze locally, and that'll give you the optimal gain. He's right and he's wrong. As I'll explain. So the problem is if you take, where is it? Where's my G? Rho equals 1. Which G is this? Right there, right there. Yeah. So the top, where's my G though? No, but it's probably the next slide. Oh yeah. All right. So this is slope -4. If you go back to the work of Rupert in the 80s, it'd say, the optimal G is 1/4, because you want to make it so that instead of a slope of -4, a slope of exactly -1 is optimal. And it's optimal in terms of the covariance, the asymptotic covariance. But a gain of 1/4 leads to that. Unfortunately, this is scrambled a bit late. Sorry about that. It leads to this, the ODE converging at rate n to the -3/4. Oh, I see. Excuse me. I'm sorry. I got confused here. This is for any G. His G is 1/4, and you get this unacceptable convergence in the ODE. And so you end up tracking something you don't want to track because it's so slow. That's the point. All right. And so in order for this to go fast enough to deal with the bias, you got to make G bigger than 3, because you want to say make this go to 0 like 1/n. So it's just vanishing faster than anything else. But then Rupert would say, no, you're making the variance big. That's for step size G/n, okay? G/n. And so that's the trouble, is that I'm having trouble transitioning, because I was raised in that point of view, that 1/n step sizes, choosing the optimal potentially matrix gain, and then you're done. But that's only looking at the asymptotic statistics and ignores bias. And so the bias can go to 0 so slowly, it's ridiculous. And it's all because of the damned ODE. All right. And here's a really good plot to show this. So I'm sampling the ODE and the stochastic approximation algorithm for the same initial condition at 100, just so you can see the deterministic behavior. And if you take rho equals 1, then after a million steps, the time is only 2.8. You've only gone 2.8 seconds. After a million iterations. So people say Q-learning is slow. It's not slow if you do things right. It's slow because for Q-learning, tau n after a million steps is a microsecond. What's less than a microsecond, a nanosecond? I mean, you end up getting with the way it's presented in Watkins' paper, this tau n is just completely doesn't move because of the fact that there's a 1/n step size proposed. Now, if you take rho equals 0.9, it's better. You get up to 5 seconds. If you take it 0.8, you get all the way up to 10 seconds, and you see, I've done it. Right? So making rho small is a good thing, and whether it's 0.8 or 0.7 or 0.6, go for it. I don't know. My grad student Aditya Devraj loved 0.85. I have no idea why. I would go for 0.6. All right. Now, it turns out that if I don't start at 100 and I start at 0, which is the optimal, which is the root, that's theta star, then Rupert's right. I do multiple runs. I get a beautiful histogram that looks exactly Gaussian. I see the covariance is exactly the optimal covariance, same as averaging. It's all fantastic. But I don't know theta star in advance, so I can't do that. Okay. So here's what happens. So all these histograms were all done with the same initial condition at 0. So I'm cheating. But if you take rho equals 1, the little sigma theta standard deviation, 5/2, that's the optimal. That squared is the optimal Polyak-Rupert covariance. And 1/4 is the optimal. If I choose this thing that gets rid of the bias, believe it or not, that standard deviation is a little bit bigger, but it's not much. But if I take any of the rho and do the Polyak-Rupert averaging, they all look identical. So again, never use 1/n. Use a smaller rho average, and you're doing great. You're taking care of transients and the steady state. Hopefully that's clear. Now here's something that has been a standard joke of mine for 20 years. I bet this has happened a million times where a graduate student has run into his or her advisor's office and said, my God, look at how awesome this algorithm is. It's just, there's a little bit of wiggling there, but look, it's just locked on to the optimal value. Q-learning is so efficient. And then you learn that no, it's over here. Okay. So this is basically running Watkins' algorithm as is, just picking up his paper, coding it up, you'll get that, and that's a million samples. And so when people say Q-learning is slow, they're referring to that. So when you run any algorithm, stochastic approximation algorithm in RL, you want to see that. You want to see volatility because you want to see it crashing over in the right direction. And you want it to wobble around a lot because you're going to average out that volatility in the end anyway. So I'm going to average out from here to here, and I will basically get the answer. Right? So you want volatility. Okay. I mean, of course, if you're looking at a deterministic problem, that's not the case. If you're looking at, like the problems that Bert was talking about, applying Q-learning to solving a deterministic optimal control problem, and you're not introducing stochastic noise for exploration, so everything's really deterministic, then you wouldn't really see this. But most of the examples we talk about, we have these Markov models, and you expect volatility. Well, ask for it, because you need high gains, results in high variability, then you average, get rid of it. Okay. Oh yeah, that's what's funny. So, Aditya graduated in 2020, and his entire thesis is about 1/n step sizes. It's like we didn't appreciate how valuable averaging is, even though we were aware of it. And the main focus was on dealing with these awful dynamics. See, I mean, the reason this happens for Q-learning is that in Q-learning, the tabular Q-learning, this A matrix is Hurwitz, but it has an eigenvalue at 1 minus gamma, where gamma is the discount factor. And that's what causes this very, very slow conversion. You know? And that's why Rupert would say you'd have to have a gain of 1 over 1 minus gamma to, to kill that off and get the, a decent rate of convergence. So his work was focused way more on dealing with rule 1, dealing with the nonlinear dynamics, the deterministic dynamics, and not as much of the statistical aspect. I'm just going to pause for a second because I'm sure there must be either you're asleep or you have questions. So. You got the 3 rules. There will be an exam. Okay. What about a situation like Q-learning with function approximation where there's no theory? If you're looking at Q-learning, I mean, there's special cases for this theory. Like if you look at these linear MDPs and you assume you know everything, then it's like tabular Q-learning. And there's Q-learning with binning where there's a theory. But if you just take a neural network or a linear function class, there's no theory at all. There's lots of counterexamples, but only in the last few years there's been some theory for stability and convergence. So what do you do then? And so that's where this Pokemon character comes up. All right, so we're just going to go through this and we'll stop. Now, remember our goal. Remember our goal? It's a root finding problem. I don't care about theta at all. I don't care if theta converges. All I want is that f bar of theta converges to 0. And so what you can do is you can treat f bar as the parameter and try to design a vector field so that this is a stable system. And this is such a good example of where we can do anything. There's no gravity, there's no physics. I just need to solve a control problem and then I can translate it to an algorithm. Now, anybody think of a vector field that's stable and makes f bar go to 0? That f bar t is, Anybody think of a linear system? Make it linear. You could just take V to be V of f to be minus f. There would be this linear system where A is minus the identity matrix. All right. So if you do that, you can solve that and you'll get that. That certainly goes to 0. So f bar of theta t is f bar of theta 0 times e to the minus t. And we discovered this on our own, and then Vivek Borkar pointed out to me that Smale did this in the 70s. Of course. And we knew that somebody else must have thought of this, but they didn't do it in this context. It was actually some economists who came up with this, and then Smale analyzed it, not for stochastic approximation, but just for solving root finding problems. Okay, so there it is. Now, of course, that's not an algorithm, right? But to get an algorithm, we need a differential equation for theta t in the end. But you all remember the chain rule, all right? If you go and apply the chain rule, that is equivalent to that, all right? So I go through and I say that the derivative with respect to time of f bar of theta t is the partial, yeah, it's up there, next page. Where'd it go? Where's 8 bar? Ah! These slides keep evolving. So before I looked at the linearization at theta star, now I'm looking at the linearization at any value. So the translation of that to a recursive algorithm is what we call Zap stochastic approximation. And that's universally stabilizing, so this should be as well. And there you go. Now, translation of this to a discrete time algorithm, you really have to read the second chapter of Borkar's book really, really carefully. And that's not an easy task, so I'll explain. Because it's complicated because I have to estimate this matrix and estimate this and At first sight, that's not obvious. All right, so here it is. Let's go through this slowly. So the first, that's the ODE approximation for this ODE, right? That first line there. If that A hat is an approximation of that A of theta t, can you all see that this ODE and that first line, they look the same, right? This looks like a noisy Euler approximation of that ODE. Yes, now you're asleep. Does it? Okay. I mean, the issue is that that matrix is supposed to track A of the current theta. That's what's really, really tricky, What you've got to do is you've got to run something that looks like my Monte Carlo. So it looks just like this. Where to go? Oh, it's not here. The stochastic approximation version of Monte Carlo. I'm trying to compute a mean. Oh, right there. So if this was 1 over n plus 1, I would just be trying to compute the mean of A. But A depends on theta, so I can't do that. So what you do is you stick in a step size here, which is big, much bigger than alpha, because we're trying to do a tracking problem. We want A n plus 1 to be approximately A of theta n. And theta n is moving slowly. This thing has to move much faster to track. Okay, and that's it. So basically, to get this approximation, that this matrix here approximates A of theta n, you just have that. You just need beta n over alpha n to go to infinity, pick up Borchar's book, chapter 2, you're done. And as it turns out, all the Lipschitz continuity conditions hold if you're clever in how you define things. I got to be a little careful there, but I'm not going to get into it. So this is magic. I mean, it's just absolutely wild. So you slap this onto Q-learning, as we will, and it just works. and it works, incredibly well. Now, here's the one case will allow you to use 1 over n, because as it turns out, with 1 over n over here, this looks very much like Rupert's original sort of algorithm, where he didn't do this, he just shoved in A star inverse, the linearization of theta star. Now his algorithm, you don't know if it's stable, it could have terrible transient performance and everything like that, okay? But he argued that gave you the optimal covariance, okay? So because of the fact that that matrix is going to converge to my A of theta star, that converges to Rupert's matrix gain, okay? For which you can use a step size of 1 over n. So it's perfectly fine if you exactly do this, to use 1 over n here, and then beta n say something like this. You note that I wrote between 0.1 and 1. That's because his slides are dated by 6 months. So you can let rho be 0.1 and it's fine. No, it's not going to hurt you at all. And so it's, yes, again, with that choice, alpha n equals 1 over n, you get the optimal covariance, universally stabilizing. Of course, you can see some issues that could come up. And the theory is quite simple. It's not that hard to prove things. You can imagine what could go wrong is, that inverse might not exist. And what you really need is that when this is not invertible, f bar of theta can't be 0. That's the condition. So whenever this inverse does not exist, f bar of theta cannot be 0. And then you can show that this still works. The ODE still converges, as long as you replace the inverse by a pseudo inverse. And numerically, kicks ass. It just, somebody needs to help with this. On MATLAB, it's never failed us. It always works. On Python, it doesn't. There's a finance example in Aditya Devraj's thesis. When we try to convert the code to Python, the pseudo-inverse code in Python is so numerically unstable, it just wouldn't work at all. Because you don't really invert this, right? I mean, you solve in MATLAB, it's A/B. You just solve the linear equation. Now, so yeah, just in conclusion, I will always be grateful to Lyapunov and Polyak. Step one, design the dynamics. Step two, if I were you, I'd stick to bigger than a half for the bias issues I talked about. But yeah, you don't want to, you don't have to. But no rho equals zero. You're not allowed. And then always do averaging. And then you'll get this wonderful covariance matrix. And basically repeat, because you're going to do a bunch of runs, maybe with n equals 1,000, get a histogram, and then go off and say, with n equals 1,000,000, I have an approximate confidence interval, and that's it. And one thing that I used to really make a big deal about this, when you do repeated runs to make sure the initial conditions are widely dispersed. That's in the old days when I was using step sizes of 1 over n, because I was sort of immersed in this, old-fashioned culture. And now, if you choose like rho equals, point, I don't know, 0.6, the transients go to 0 so quickly that maybe it's not so important. It's only if you take rho close to 1 that you have to worry about transients more. So make the initial conditions a little bit dispersed. And then, and that's the thing, is that that's what you're going for. You're going to use this heuristic in the end. Once you estimate this covariance matrix, you'll use this and say, well, if I want a probability of error of blah, 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 I'll use this heuristic because it's all I've got. I don't have that. I have that, a heuristic. I don't have that B or that I of epsilon. No chance. But something useful, you know what I mean? I mean, for finite states with Markov chain, they do exist, but they're so conservative, I would have to wait 1 trillion samples to get the probability error I want. So it's, it becomes a heuristic as well. Yeah, so I've got some more time, but I'm not going to use it. I'm going to, the next lecture is this sort of control crash course, which thanks to Deb, I don't have to, I don't have to, I can go pretty quickly through it. I'm going to go through about how to apply this to RL, how it works. One second. Yeah. Yeah, so if you, I've got these slides are there for you. If you want to understand the variance formula, why this approximation leads to those formulas for the covariance, the whole thing is here. You can take a look. Yeah. All right. I think that's good. I think an hour and 15 minutes is enough for all of us. Questions? Well, yeah, I think you were first. Okay. Yeah. Yeah. Well, it's just, yeah, the A/B that is somehow it's buggy in Python. And yeah. It's and the last time I tried, it still was true. Yeah. Yeah. Oh yeah. Well, yes. If we in Python, what we ended up having to do, if the matrix was singular, was to use a epsilon perturbation of the inverse. I forget what it's called, but there's an approximate pseudo inverse, and that worked fine. But it is strange, isn't it? It's just strange that we never had a problem with MATLAB. And we look at these high dimensional problems where the condition number of A, if it wasn't 0, it was, horrible. I mean, if it wasn't infinity, it was horrible. And it always worked in MATLAB and it never worked in Python. It was just really, really amazing. I'd like to understand that. And so you have which one? Oh, here, yeah. Okay. Oh, yeah. Okay. Yeah. That's right. So I know I could spend half an hour on this slide. I'm trying to approximate that OD. And if I had this, if I had access, if somebody gave me that function, the matrix function, I would just cram it in there and write A of theta n inverse, you know. Yes, I'm trying to estimate A of theta n for the current theta n, which sounds very ambitious. But there's this beautiful theory of 2 times scale stochastic approximation that says that as long as I crank up the gain here, then you can show that we will get exactly the approximation that we want. It's beautiful. Yeah, yeah. No, that's what you don't. Yeah, you don't at all. I mean, you know, so DTF found marginal improvements, by playing around with different rows. Maybe it's here where he took alpha n to be 1 over n, and he ended up, this is it. This is where his favorite choice was 0.85. But there, I mean, we tried different rows. I think that was just, he liked that number for some reason. I don't think it matters at all. I really don't, I really don't think it makes any difference. I think, I think taking it to be equal to 0.6 or whatever is good. I mean, we didn't try it because we didn't have the courage, I don't think. But, 0.1, I think would be fine. I think, no, but let me be careful here. What goes wrong is that, oh yeah. So here's one reason why you should make rho too small. Because remember my warning about constant step size, because choosing the right constant step size is really, really hard. You make it too big, it's unstable. Make it smaller and smaller and smaller. Eventually, phew, it's stable, and it's a lot of work. And then what's the benefit? It doesn't improve anything. Just let the thing decay because it's not going to hurt your rate of convergence in any way. But if you make rho 0.0001 or whatever, then it's like a constant step size. It'll take 1,000,000 steps for it to get small enough. So what's really nice about a step size of this form is that you're sort of learning a decent gain. And so what's going to happen is when you run this code and you take where's the general formula? Yeah, if you take G too big, it's just going to blow up. You're going to start off at theta, a vector of zeros, and after 100 iterations, it'll be 10 to the 10th. Now, I used to say 10 years ago, oh, put a projection. No, your step size was too big. Just reset. So create a ball of radius 10 to the 10th, or whatever you like. I don't know. Whatever you think is a ball is big enough. Whenever it hits the outside, reset to 0, because all that data, all the things is garbage. You haven't learned anything. And so you'll reset. This thing's decaying. Eventually, it'll stop resetting. So there's a learning there that takes place. But if rho is too small, you'll reset forever. So that's why you should make it too small. And that should be rule 4. No projections reset. I mean, in this context. I should say, when it comes to ZAP, what's really fun is there are ways to, again, control. You can go through and create so my theta is d-dimensional. You can stack up and create a 3D, d plus d plus d dimensional dynamical system that ends up being universally stabilizing and approximates this dynamics without any matrix inverse at all. It's really cool. Now, when I code it, the performance is not great, but it just shows that there's a lot more we could do. There might be ways to really get nice, robust algorithms without the matrix inverse. The theory works. I know it converges. I know it has all the right properties, but just I find I get massive excursions and stuff. There's some weird dynamics. So there's a lot of work to be done with this to make it more efficient. Yes, it is. No. Yeah, no, this, once you defined F bar, you've got an A. But I mean, yeah, no, we get to do so many things with F. So we can change F bar. Like I mentioned, a division by subnormalizing constant to make it Lipschitz, or the introduction of a matrix gain. And I could consider that product to be my new F bar. And as I just mentioned, I can construct this. It was originally d-dimensional. I'll correct it, create an OD that's 3 times d-dimensional that has this universal stability properties. And basically doing feedback linearization, but more smoothly than this, not directly. So yeah, we get to design F bar. That's a fun that the Russians acknowledged again in the 60s, and it was sort of rediscovered, not by me, but people have been pushing that for the last decade. Yeah. I mean, I think it's the biggest reason I wrote the book was to sort of push that idea that we could design the dynamics in this simple continuous world. And I also, I mean, I've got this mission to try to push back against finite inbounds. Sorry to some of you. We can have a friendly debate. I know the context will really make sense. I'm just saying, acute-learning, it doesn't. I really don't think so. Mm. All right, so let's have coffee, right? Okay.